Today, we are diving into a really powerful tool. It's one that helps you move from just plain guesswork to a data-driven strategy. It's called multiple linear regression, and it's how the best analysts and leaders quantify really complex problems to make precise, high-impact decisions.
Just think about that for a second. What if you could understand not just what's going to happen, but why it's going to happen? And more importantly, which levers you can actually pull to change that result? That is the strategic capability we're unpacking today.
So here's our game plan. We'll start with the core idea. What is multiple regression? Then we'll get into the strategy of it. When do you use it? From there, we'll decode the formula, piece by piece. We'll also cover the 4 key assumptions you absolutely need for a reliable model. And finally, we'll see how it all works in the real world. Let's jump in.
Okay, first things first. Before we can talk about how to use this thing, we need to be crystal clear on what it is and, what makes it so different from simpler methods you might already know.
At its heart, multiple linear regression is all about understanding relationships. The key thing to get here is the structure. We use many different inputs. We call them independent variables, or x's, to predict one single outcome. That's the dependent variable, or y.
And this slide right here, it perfectly shows the leap from simple to multiple regression. Look, simple linear regression is great for a one-to-one relationship. But let's be honest, the real world is almost never that simple, right? Multiple regression lets us model that complexity, analyzing how a whole bunch of different drivers can all influence a single critical outcome at the same time.
So, we get the concept. Now for the million-dollar question for any strategist. When do you actually pull this tool out of the toolbox? Let's talk about the specific challenges where this thing provides some serious value.
You're going to turn to this method when your reality is complex. When a critical outcome like your quarterly sales or your manufacturing yield or even customer churn isn't driven by just one thing. It's for those times when you need to untangle all those different influences and see exactly how much each one is contributing to the final result.
And this is a perfect, tangible example. The final price of a house is our single outcome, our why. But what drives it? Well, it's not just one thing, is it? It's a mix of all these X variables: the location, the square footage, the number of bedrooms, the age of the house. Multiple regression lets us build a model that takes all of these factors into account to predict the price.
All right, let's pop the hood and see how this thing actually works. Now, the formula might look a little intimidating at first glance, but I promise we're just going to break it down piece by piece. Think of it like a recipe for our prediction.
And there it is. This is the blueprint. It's called a first-order model, which is just a fancy way of saying we're assuming a straight-line relationship between our inputs and the outcome. It might look complex, but really it's just a bunch of stuff added together. Let's break down what each symbol means.
So first up is y, the dependent variable. This is our target. It's the one thing we're trying to predict. In our house example, y is that final sale price. It's the destination we're trying to get to.
Next, you've got your x's. These are the independent variables, the inputs, the causes, the drivers. For our house, the x's are things like the number of bedrooms, the square footage, the age of the house. They're all the ingredients that influence the final outcome.
Now, this is absolutely critical. The beta coefficients are kind of the secret sauce here. Each x variable gets its own beta, and it basically acts as a weighting factor. It tells you how powerful that specific ingredient is. So a beta might tell you that for every one additional bedroom, the house price goes up by, say, $20,000. It quantifies the impact of each driver. And finally, we have epsilon, the arrow term. Look, no model is ever perfect. Epsilon, or the residual, represents all the random noise, or maybe the factors we just didn't think to include in our model. It's that unavoidable gap between what our model predicts and what happens in messy reality. It's what keeps our model honest. Okay, now, before you can actually trust your model's predictions, you gotta play by the rules. And these aren't just, academic suggestions. Think of them as a professional's checklist to make sure your model is reliable and robust. So there are 4 big rules you have to follow. Think of it as quality control for your analysis. First, the residuals have to be independent, meaning the error for one data point doesn't predict the error for another. Second, and this is a big one, no multicollinearity. That's a mouthful, but it just means your input variables, your x's, shouldn't be too similar to each other. Like, you wouldn't use both square footage and number of rooms because they basically measure the same thing, size. If you do, the model gets confused. Third, the residuals should be normally distributed. Just a quick statistical check to make sure the errors are random. And finally, linearity.
The whole method is based on the idea that the relationship is a straight line. If it's actually a big curve, well, this model isn't going to be very accurate.
The big takeaway here is that these assumptions are what give your model integrity. They're the difference between a model that's a house of cards, ready to collapse, and one that's a fortified castle of analysis that you can confidently use to make big decisions.
All right, we've built the model, we've checked the rules, so now what? How do we actually measure its performance and apply it in a real-world setting, like in a Six Sigma project?
The very first thing we look at is a metric called R². The easiest way to think about it is as the model's report card. It's one single number that tells you how good your model is at explaining the outcome. It's the percentage of change in Y that's actually explained by your chosen X variables.
And R² is always a value between 0 and 1. You can think of it as 0% to 100%. This simple scale is what makes it such a powerful and easy way to communicate how well your model is performing.
So an R² of 0 means your model is completely useless. Your variables have 0 predictive power. An R² of 1 means your model is a perfect predictor, which, by the way, almost never happens in the real world. So generally, the higher the R², the better your model fits the data.
So let's look at this real example. Say a chemist wants to model a process yield. The model gives a base yield of 31.37. Then it tells us that for every 1 unit bump in factor P, the yield goes up by 0.75. And for every 1 unit increase in factor Q, the yield goes up by 1.5. And just like that, we have a clear, actionable formula to optimize this entire process.
And that right there is the ultimate power of this tool. It takes you out of the world of hunches, and I think this might work, into the world of data-driven decisions. It lets you quantify these complex relationships and understand exactly which levers have the biggest impact on the things you care about most.
So, I'll leave you with this question. What's the most critical outcome in your work, or hey, even in your life, that isn't driven by just one thing? And what are those multiple factors behind it that you could actually start measuring today to build your very own predictive model?